Welcome back, everyone. This is the first video about functional patterns, and today I'll cover map and bind. In the last video, I talked about the container data types at a very abstract level, and result data type and option data type. And I also mentioned that I call option and result as option container and result container. The for me the result and option types are container data types. Just like a list is a container data type, a sequence is a container data type, a computation is a container data type. So it helps me to generalize and break down things into broad areas. It helps me visualize problems and solve problems more effectively. Now, functional patterns, as I mentioned in the previous example, the previous video, are all about container types and, depending upon the container type in question, certain functions. So I begin this blog by mentioning the problems that there are with learning functional patterns. And the very first reason I'm mentioning is that the whole terminology in itself is a problem for people like us. We don't have that mathematical theoretical background, category theory background, or functional programming background. We don't understand these terms. So as we move forward, you will understand these terms. That's a process in itself. In functional world, there are no classes, interfaces, inheritance, etc. It's just container types and functions. So when we look at let's say a factory pattern in C sharp in Java, and there are infinite number of patterns in that world, there is a certain method to the madness there. The method here is completely different. So you can't scan patterns and functional world with the same view. You need to change. There's a drastic change in approach that's needed. And thirdly, partial application makes everything more and more complicated, at least to start with. You have to carefully examine what is going on, what is partial application doing in various cases. So here is an example that what I mean by this third statement, because this in particular was a major hurdle for me, because I would in past I would study something and then check out some other examples and then study something else, and there was a mismatch in what I was studying via multiple sources. So here's an example to illustrate what I'm saying. Now here's a list.map function. I've lifted this from F# documentation. So this list.map function, which takes two parameter mapping and list. So mapping is a function, you can see it, which does t to u. T could be any data type, u could be any data type. And the second parameter list is a list of type t, and what it returns is a type of a list of type u. And you can check out the documentation. It says builds a new collection whose elements are the results of applying the given function to each of the elements of the collection. It sounds, if you study the description of the function, it sounds as if this function is going to return a new list based on an existing list. You supply a list and you will get a new list by via a mapping function. So we'll talk about what is mapping later. And this is another description available on the same site, which is full usage, this, the function to transform elements, the input list, the output list. Now, and this is where I lifted this from, okay? So you can check out all functions available for the list container type here. Now, this is the signature of the list.map function, mapping t to u, first parameter, list, second parameter, third parameter. And as I've tried to explain here is, So far so good. You may not really understand what is map function doing, but you keep on studying, you check out the examples, and then eventually you figure out that, oh, it's nothing but the select method. There's a select method in C sharp link. You have any enumerable, you can run enumerable dot select, inject a function, get a new list or a new enumerable out of it. Okay, and so far everything is fine. You are struggling, but you are evolving. Slowly you are building and building and building, and you have developed some kind of understanding. Here's a list container type, and here's a mapping function which can produce a new list out of an existing list via a mapping function. And then you study more, and these are the two statements I am 110% certain you will encounter when studying about map as a functional concept. Go and study map, you will definitely encounter these two statements, that A, map returns a function, and B, map lifts a function. And at this point, it's a total collapse. The whatever you studied so far, that mm, list.map function was generating a new list for you, has no connection with these two statements. And this is where everything is of, at least for me personally, there used to be a complete crash, head-on collision with two uh, distinct ideas, and how to make sense out of it. The big issue here is, going back to the previous list, this is one issue, and this is another issue, and the third issue is, oftentimes when people who are experienced in functional programming, their perspective is slightly different, and their perspective is because it has evolved over usage of many functional patterns. They look at things differently, and not it's not magically differently. Oftentimes it's because of the partial application. So always remember, partial application returns functions. Partial application is not the end of a function call, it's returning a function. So if you look at this function, and if you call this function with just the first parameter, you will end up with another function. And it is a complicated it's a complicated situation to start with. When you're learning, it can get overwhelming. The signatures, the partial application, and all sorts of abstracted ideas, they stack on top of each other, so it can get overwhelming. So I'll do my best to explain to you what is happening. And the whole idea of partial application is not for an academic purpose, or you can generate a function by partial application and have fun with it. No, there is a reason. There is a strong background, but let it happen. Take it very slow. Maybe in case you have to go through all of this twice, let it happen. Okay. I've said this in earlier videos also, that functional patterns are evolved based on repetitive occurrence of problems, repetitive occurrence of solutions, and then you capture repetitive ideas into data types, container types, and functions. So, no surprise there. This is one thing I wish to spend some time on, and this is where I personally myself in some kind of terminology or lingo clash. Now, I am not a category theory person, nor am I a Haskell person, or nor am I a mathematics background person. I attack problems in a very programmer way. So the term elevation and lifting is, if you go and study thorough documentation for category theory or functional programming, you will find these terms have a very situational, very specific meaning. But for my purposes, I have a different, slightly different, not drastically different, slightly different usage is what I have evolved for myself. And here is my version. I'm pretty certain it can help you fast track everything. Lifting and elevation, I use these two terms synonymously. I don't use these terms differently, or in a certain case, I don't say, oh, it's not elevation, it's lifting, or the other way around. For me, lifting and elevation is one idea. And here is my version. Lifting and elevation can happen in two areas. Area number one, when you are talking about lifting data. So, very, very simply put, let x equals to 10. X is an integer and x is real data. In other words, x is not lifted, elevated. That's when you are dealing with data, that's bullet point number one. Bullet point number two, let y equals to sum x. What we are doing is we have real data, we are lifting it, getting elevated data. So whenever, no exception, when you're not talking about regular data, and regular data covers everything from primitive data types to records to discriminated unions to enums, anything which is your data. When it is lifted into a container, when it is elevated into a container, it's elevated. Y is an end option. Y is the reason this classification is needed is because you need different functions to operate on this data. If you have a function called let add 2x equals to x plus 2, this function can operate on this, but this function can't operate on y because y is an int option. Y is not an integer. You can't say let result equals to add to y. This won't work. It will say int was expected, but you are sending an int option. So why this classification is needed? Because in future you will create and or deal with functions that operate here or here, that deal with elevated data or that deal with the data that's not elevated. So far data is concerned, this is exactly what I'm talking about here. Lifting, elevating, packaging, storing data into a container, that's lifting. Int goes into an int list. So here is another example. X is 10 and let y, or let me call it z. Now z is an int list and x is an integer. You need different nature of functions in order to operate on integer and on a list of integers. You can't use same functions, okay? And lifting, elevating functions that operate on regular data types. So a function that operates on int. So where things get completely obscure is lifting data is easy. Here is one example. Here is another example. But if you want this function to start operating on this, you will have to write another function which understands int options or int a result which has int on the OK side, or a function which understands a list. So lifting for me is when you write a function which operates on real data. You are operating on X here, and you do some magic, not rewrite or write a different function altogether. You do some magic, and that function starts operating on options. So imagine this: let add to for option x, which is an int option, equals to whatever. We don't care about the body part of it. But you can clearly see that add2 operates on integers and add2 for operation operates on this. But in this case, I have done the hard job of defining a function which operates on int option. Assuming that there is something of sense written here, you can assume that I did the hard work, I did the heavyweight lifting. The burden is on me. So when you say lifting a function, you're talking about not doing this. Instead, you're talking about using one or a combination of techniques to extract, create, compose a function without writing, which converts this into this. We will see how, we will talk about it later. But that's the overall idea. I'll quickly repeat myself so that there is no confusion. Data is either real data, normal data, or it's either lifted data. This is your real data. Sorry, this. This is your lifted data, elevated data. This is option example. This is list example. The moment data goes into a container, it's packed into the container. So packaging, storing, lifting, elevation, when it comes to data, I use these terms. Not only use these terms, for me it's just three things, four things: data, elevated data, regular function, elevated function. That's it. I use the all other words I use freely. And so those are just four nature of things. I have data which is real, I have data which is elevated, I have functions which operate on real data, which is int, string, float, my records, my discriminated unions, my whatever, not discriminated unions per se, and functions that operate on elevated data. So this is what I've tried to explain here, and I've also given an example that in C sharp, let's say you have a function called double my int, which returns times 2 of the given number, and here you are calling this function. Now you need to double all the int values in a list, which is the same example that I was talking about. That you have a function for operating on int values, but you don't have a function for operating on int option. Similarly, here you have a function for operating on ints, doubling the values, but now the problem statement has changed. You have to now operate on list. So to illustrate, I created two functions, double my int and double my int list. In this case, I'm returning x into 2. In this case, I'm creating a new list. For each item in that list, I'm resulting a new list with all the values doubled from source to target, etc. And then I have explained more and more that using link, you can simply write this, which is the functional way of doing it. This is one way of looking at the situation, that you don't need to create a new function, you can solve the problem one way or the second way or the third way. What function lifting is not this. This is using link to solve the problem in an easier, effective, and one of the best ways possible in C sharp fashion. Lifting a function literally means do something, and you can actually say let this equals to something done with add2. When you understand this, that's lifting a function. You write once and create versions out of it, for the lack of better expression. So just go through this section where I've also explained the same issue in different ways, and same thing, what I mean when I say lifting of data versus functions. and real data versus real functions. So now I'll first of all begin with the map functions, one of the most heavily used functions in the functional world. And before I begin with map, I'll explain something. Mapping in functional world is a super generic name for transformation. So select, project, transform. There are too many names and symbols. That's another problem you will face in functional world is it's just full of symbols. And sadly, F sharp doesn't really accommodate symbols too well. Something we will discover over period. Uh, F- in Haskell, the operators and symbols are different. In F sharp, operators and symbols are handled differently. So map is a very straightforward idea. So first of all, let's understand what mapping is at a very raw level. So if you have a value and if you have a function that operates on that value, and at this point in time ignore the mathematics of it and the laws of mapping and functors and so on and so forth, just ignore it. It's not really something you need to be worried about right now. Get a feel of map as a concept and slowly everything will make sense. Decorate your understanding later, complicate it later. Don't get into all those fancy things right now. So add 2. So if I say let y equals to add 2x, what I'm doing is I'm saying, hey, add function add 2, take my x and give me your output. One of the very don't look at add 2x in an imperative way. Look at it as a transformation. You called a function, you supplied a value to that function, you got an output. To help you visually, I can say this add 2. That should help you with a slightly better visual. Input goes through a transformation, output. At a very low, raw, unrefined level, this is what mapping means. Full stop. You take something, you give it to a transformer, and that transformer produces the output. So now let's move towards options and see what happens with when we talk about mapping with options. So I'll just create two options. Let opt1 equals to sum 1 and let opt2 equals to this, and I'll create a function let add 2x equals to x plus 2. Sorry, I needed none here. And I also do a print so that it helps you see the results, and that's helpful. So at this point, OPT1 and OPT1 is in some state, some case with 1, and OPT2 is in none case, and remember options, none has no data associated with it. Now the problem statement is this is optional data placeholder container, and what you need is this. Whatever is inside the container, add 2 to it. So you may say, all right, one way is let result equals to, because you understand pattern matching, you may say match, and I'll call it result1 opt1 with, if it's in some case, I'll say x plus 2. If it's in none case, I'll continue with none itself. What happened? What? Oh, oh, I'm sorry. So we are doing a pattern match on option. If it is in some state, the value is x. We are returning a new option with x plus 2. And if there is no data, what can we do? So we return a none, and we do the same jazz for OPT2, and we call it result 2. And let's print result 1 and 2 now. And let's see what happens. Oh. So sum 1 became sum 3, none remained none. The reason we couldn't use this over here, we were forced to write so much piece of code, is because our add2 doesn't understand option. Our add2 only understands raw numbers, integer values. And this is where mapping comes in. Mapping is, if you have a container, doesn't matter what the container is, and if you need to transform the value inside it, container plus that container's map function will solve the problem for you. So I can instead of doing this, I can say let result 1 equals to option dot map add to opt1 opt1 and result 2 equals to option dot map add to opt2, and let's just reprint everything and see. So this produced the same result as this: sum 3 none, sum 3 none, and no surprises. Option dot map, don't bother about the documentation right now. All it does is it takes the option you are supplying, the overhead, the extra job, the structural awareness, how to extract value out of an option, and then do whatever. And if you pay attention, I am doing multiple things here. First of all, I am extracting the value out of option here and here, and then I'm applying my business logic, which is x plus 2, and then I'm repacking the whole thing back into a sum. Too much burden for me. I don't need all this. This is my problem. My problem is already programmed. I need somebody else to take care of this nonsense. And that's where option.map comes in. Here is your function, here is your container, and here is your business logic. It may seem silly or inconsequential at the moment, but largest of the problems are solved by nearly just a dozen of mostly a dozen of functions, maybe 2 dozen, maybe not more than 3 dozen functions. That solves more than 95% of the problems. And that's arguable, but so let's not go there. But option.map is whatever is inside the container, transform it. If it can be transformed, which is happening here also. If it is in some state, it can be transformed. If it cannot be transformed, move on. You can implement your own map in a very simple, similar fashion. And we will do it perhaps later. We will write our own functions to get a stronger feel for what these helper functions with container data types do. But at this moment, just pay attention to what's happening here. You create a function and you call option.map, which is the function for option container, give your function, which is your business logic, and the container. Option 1 is the container, option 2 is the container, and you get the result. And that's what map does. The critical thing that you need to observe here is that option.map is allowing you to use this function. You wrote your function to operate with data that was not elevated. That's the key to focus, remember, swallow, and let it marinate in your head. Option.map allowed you to take an option and a function which operates on real data. This is elevated data. Option 1. This is elevated. And this function is operating on real data. And option.map is doing the magic of letting you use add to with option 1 and option 2. This is very similar to link. This is similar to the example that I was showing you on the blog. We have not covered lifting of function as of yet. I'll just do it in another 2-3 minutes. One, real data packed into option elevated data. None, option 2, elevated data. Add to is your business logic. It could be as simple as that. It could be 100 lines of code. It could be an outcome of composing or partially applying complex series of functions. The philosophy doesn't change. Only the size and vastness changes. Add to, still operating on real data. Option.map is enabling you to use a real world function with elevated data. That's the beauty of option.map. Now, let's for a moment see the documentation of option.map. It says this. So I'll copy this for visualization's sake. There is first parameter, mapping, which in our case is add to. It says, give me an option of type T. Second parameter, give me an option of type T. Option 1 is an int option. So the T parameter in this whole equation is sorted out, that the T is now an integer. So we need to supply a function which operates on an int, because we are talking about an int option. And what this function will return is a u option. Now, what are we supplying when we are saying add? Add is an int to int function. So I'll also write the signature of add int to int. So this mapper of yours is int to int. This option of yours is int. So the output you will get is again an int. I'll just render another example. Num to string equals to x dot to string. Sorry. And this is an int. The way we will use it, it will become int to string. So let me render another example, int to string, and instead of this, I'll say use this method. What is happening now? Now you are invoking num to string, and num to string is dependent on option 1. So you are supplying int on the T side, here and here, and the output of this function, the mapper, is string. So what will you get out of this operation? Here you are getting an option of int, here you will get an option of string. So once again, here you are dealing with real data, here and here. You don't care where these functions are going to get used. Now I'll complicate the whole matter by I'm just bringing this downstairs, and I'll just stick to one function because this may choke you for a while. Recall what is partial application. Partial application is, don't supply all the parameters to a function. Just supply anything which is less than the total number of parameters, and you will get a function out of it. And I already explained that if you call a function with just one parameter, this will disappear. Anything before the first arrow will disappear. And what will you be left with? A new function which takes an option. Let me just get rid of this, and produces another option. So if I say let my new function equals to option.map add2, this add2 is my function int to int, and option.map when called with add2 is a partial application of option.map. So let's see what this becomes. So this becomes my new function, becomes a function which takes an option as input and produces another option as output. So this is the signature of new function. It will take an int option and it will produce an int option. So I'll just get rid of a whole lot of code that we have written to keep it simple. And instead of using option.map anymore, I'll simply say opt1, pass it to new, and pass the result to printfn %a, and similarly opt2, and let's see the results. Initially we had some 1 and none, and now we had some 1 and none. No big deal there. What you have to realize, the magic that happened here is that this partial application resulted into another function. Not a big deal. Partial application will result into a function, but what you ended up with was that you had one function which operates with real data, and my new function became a function which is operating in the elevated space. So this is where the real juice of function elevation is, that you write a function which operates on real data, use the right tactic to lift it, to elevate it, so that it can start operating on elevated data. So I can write down this as this to simplify the whole thing. I never wrote a function which can operate on options, but this is exactly what is happening here. There is no illusion, there is no trickery. Option.map, when partially applied, you have to just pay attention to the function signature of option.map, which was this. Since you supplied this much, this was supplying this much. This is exactly what you're left with. Give me one more, give me an option, I'll give you another option. That is all. So this is what I've then tried to explain on map as a function lifter, that map can be used to perform end-to-end mapping. You supply map with a function and an option, or you supply map with just a function. In first case, the full application or the application, you will get another option out. In the other case, when you're just supplying a function, you get another function out. That function is elevated version of a function that you wrote which operated on real data. So you wrote a real data function, used option.map, partial application, got a new function out of it. All right, now let's see a problem with map. I'll get rid of this much and I'll write another function. Now my business logic is something like this. Let add to if even x equals to if x mod 2 equals to, not double equals to, then sum x plus 1, no. What have I missed? So here is a function which is called add to if even. If this number is even, add 2. Otherwise, fail the operation. So it's an example of a function which receives real input, not elevated input, but produces elevated output, because all operations don't necessarily return in 100% data, success cases, and so on and so forth. This is a simple example of a function which receives real data but returns. So if you look at the signature of this function is int option. If x is workable, that is mod 2 equals to 0, we will return some case, otherwise we will return none case. And now let's apply this function on OPT1. So we have let result equals to option dot map add to if even OPT1, and let's see what result is. Percentage a result. And if you see, we have something unexpected. We had sum 1, but what we have received is sum none. Okay, this should be 2. And this is what I wanted to show you. Earlier I wanted something else, did something else, so ignore the previous experiment. So we had sum 2 to start with, and because this 2 is 2 mod 2 should result in 0, we ended up in this case. But the final result we were hoping was sum 4, not sum 4. This is a case of accidental double elevation. Double elevation is a technique we will use. I'll talk about it. It is in fact in one of the videos which is about to come. But this is an accidental double lifting. This is happening because of a very simple reason. Map is not supposed to be used with functions which return elevated data. The objective of map is use it with function which receives real data and throws out real data. If your function is throwing out real data, elevated data, then map, because map lifts the data before it returns, there is double lifting happening. I'll talk about this particular issue sometime in future, but since this video is getting already too long, what I need to highlight here is that if you have a function like this, which is conceptually different from a function like this, in one way, both these functions are receiving real data, x. This function is returning normal real data. This function is returning elevated data. If you are dealing with functions that return elevated data, you have to use bind, map's cousin. Now, I will not talk too much about bind right now, otherwise it will perhaps cause sparks in your brain. Bind is a very deep concept in itself. It covers too many areas. For the moment, just assume map and bind are cousins. Map for cases where you are dealing input, output, both are real values. Bind when input is real, output is elevated. And now let's run this example and see what happens. And we have sorted out this issue. There is a fundamental conceptual difference between map and bind, which I'll not get into right now, otherwise it will be too much information. And this is what I've said, bind. And again, I can use bind as a function lifter. I can just supply this, let my new func equals to map, nothing fancy, partial application will produce another function, and instead of this, I can do this. So earlier we did map option.map with add to lift it and let it operate in the elevated space. Option.bind with this function or such a function will elevate this function. This function add to operates on integers. This function again operates on int option results into int option. So map and bind both can be used as applications or as partial applications. Applications when you need result, partial applications when you need elevate functions and use those functions for whatever the use case is. And this is all everything that I talked about is mentioned on the blog. So like always, visit the blog. Please read carefully the details that I have mentioned. There's an error here. This should have been wrong heading mapping. I'll fix it. So that's all for now. This was a very brief introduction to map and bind functional patterns. Both are transformers of sorts, but you will, as you learn more and more, you will have a better feel for what these functions are. So I'll see you later. Thank you. Bye bye.